If you've ever looked at a really complicated physics equation, you were probably overwhelmed by the sheer number of weird-looking symbols. Latin, Greek, and even sometimes Hebrew letters all over the place in a jumbled mess. Well, it turns out a lot of that jumbled mess is really there to simplify things. In fact, most of it is actually part of one special notation. And you don't need to be a professional physicist to understand what it means and how to use it. I'd go so far as to say this is probably the single most important thing that introductory physics doesn't teach you. Of course, you saw the title of the video. You know that I'm talking about Einstein notation. Now, I won't lie, some of this can be a bit dry since all we're really doing here is notation. But there's actually some really beautiful and simple results you can get out of it, and I'll try to convey those in an interesting but straightforward way. I can also guarantee you that if you ever take any physics class that deals with vectors or vector calculus, especially electricity and magnetism, that learning this will be an absolutely invaluable resource. So what exactly is Einstein notation? To find out, let's go back to the beginning, to Einstein's paper on general relativity. There is always summation with respect to the indices which occur twice under a sign of summation, and only with respect to indices which occur twice. It is therefore possible, without any loss of clearness, to omit the sign of summation. In its place, we introduce the convention. If an index occurs twice in one term of an expression, it is always to be summed, unless the contrary is expressly stated. Well, that's a bit of a mouthful. What exactly does he mean by indices? Well, in high school, you might have been introduced to vectors, these things with magnitude and direction, where the direction differentiates them from scalars, which are just a number. Really, what we mean by that is that all you need to describe the value of a scalar is just one number. Think the temperature of the room you're in. Vectors, on the other hand, can need more than one value to describe them. Consider the displacement vector from your home to, say, a school campus. It's, say, 5 kilometers long and 37 degrees northeast. If you traveled 5 kilometers in any other direction, well, you'd miss the school. Here I described the vector with two numbers, a magnitude and a direction given by the angle, but I didn't have to do it that way. Instead, you could describe this vector by saying that the school is 4 kilometers north and 3 kilometers east of your house. You might recognize these as polar and Cartesian coordinate systems. Now, for the purposes of this video, I'll stick to using Cartesian coordinates as they are the easiest to work with when learning Einstein notation. So, looking at this, what I really did was consider the sum of two vectors, one with 4 kilometers north and one 3 kilometers east, and found that this was equivalent to just one vector which goes 5 kilometers in a particular direction. This is a really powerful tool. We can always break down any vector in some arbitrary direction into a sum of vectors in a known direction. In our case, these directions are north and east. Moving to a bit of a more abstract framework, let's label these directions to be along the y and x-axes, names you're probably very familiar with. I can now write the displacement vector in mathematical notation. Then suppose you wanted to describe some arbitrary vector in the xy plane. The general form of this vector could be written as v equals ax hat plus by hat, where a and b are just some arbitrary real numbers which tell you how far to travel in each direction. Now, thus far, I've only worked in 2 dimensions, but of course the real world lives in 3D. Moving to 3 dimensions is extremely simple. To describe an arbitrary vector in 3D space, we need 3 numbers and 3 directions. Typically, the third unit basis vector is called z hat, for the z direction. And after this point, it becomes pretty much impossible to visualize things, but I hope you can see that if we wanted to move to 4 dimensions, we just need to tack on another coordinate. And in higher dimensions, it's exactly the same. So for n dimensions, we need n numbers in n different directions to fully describe a vector. This form of writing a vector is called its component form. As we keep on adding dimensions, we can just continue on adding more symbols to match this rule. At this point, our notation has become just a bit clumsy. We have to come up with some new symbol every time we want to add another dimension. Instead, let's make the following change. Let's call x hat e1 hat, y hat e2 hat, z hat e3 hat, and so on. And we will match each of the coefficients similarly. So now, looking at the form of our vector, we can further compactify this and write it with a summation notation. We sum over all of the coefficients attached to each of their respective basis vectors. Now, say we have two arbitrary vectors v and w. We can try adding these together since e I hat equals e j hat if and only if I equals j. So we could just combine this into one sum over I. So to add vectors, we can just sum component-wise, as you would expect. You might have already known that. This was pretty simple, so let's look at something a little bit more interesting, multiplying vectors. There are two ways that you know how to do this, the dot and cross product. It turns out that the cross product really only exists in 3 dimensions, and it's kind of like its own thing that we'll tackle later on in this video. For now, we'll stick with the dot product. First, we'll look at just two vectors, v and w, in 2 dimensions. And their dot product looks, as you'd expect, you have a1b1 plus a2b2. This is just the definition of it, and it follows very simply from arbitrary dimension. You just match the coefficients and you multiply them and sum them. It should be clear then that writing this in our summation notation is very simple. For vectors in arbitrary dimensions, we can just sum from 1 to 2 to 3, but let's just stick with 2 for now, keeping this formulation in mind. We'll try to take the dot product of v and w by writing them out explicitly. So we can distribute the dot product through the parentheses. We can then pull the coefficients out front, since the dot product in each term only affects the unit basis vectors. This leaves the expression on screen. But wait a minute, by definition, we said that this must be equal to a1b1 plus a2b2. The only way for that to be true is if the dot product of each of these basis vectors obeys this. So we need, when the coefficients match, or the subscripts match, to be equal to 1, and similarly, if they don't match, it needs to be equal to 0. Generalizing to n dimensions, we then require that each of those terms go to 0. So the dot product between 2 unit basis vectors is 1 if the indices match, and 0 if they don't. This property is so important that we give it a special symbol. It's called the Kronecker delta, and it's defined in exactly the same way. Using this definition, we can write the dot product between 2 vectors like this, where since we have the Kronecker delta in there, all of the terms with I and j mismatched will go to 0, leaving the correct result of the dot product. In fact, because we filter out all of the cases where I equals j, we really can just replace j with I and get rid of the Kronecker delta, and then with that, one of the sums. This just gives us one sum over ai bi. It's at this point that we are finally ready to understand Einstein's shortcut. He noticed that whenever you have some vector expression like this, there are 2 rules which are never broken. Firstly, if an index in a sum is repeated twice, so like the I in the dot product equation, then invariably that index will be summed over. So Einstein just decides to drop the sum altogether. Where since the index repeated, we simply know implicitly to sum over I. Of course, there is some context needed to know what dimension we are in, but that will typically be provided, and as long as we remain in this abstract notation, we actually don't even care what dimensions we are working in. We can just leave all of that to the notation itself. The second thing Einstein noticed was that an index will be repeated at most twice. If you ever see an index repeated 3 times, then something has gone horribly wrong. For example, the expression ai bi ci just doesn't make any sense. This rule serves as a very useful check to make sure you haven't made a mistake in your calculation. So with just these 2 rules and the use of the Kronecker delta symbol, you really can do quite a bit. There is actually one more crucial symbol that we should introduce though. So I'll introduce this final tool, the Levi-Civita symbol. So far, using our notation, we have the components of the vectors, the coefficients attached to the unit basis vectors. These have one index, and I just introduced the Kronecker delta symbol, which has 2 indices, and filters for when those 2 indices match. The Levi-Civita symbol is one which has 3 indices. Each of the indices can take on the values 1, 2, or 3, which often correspond to the x, y, and z axes. Then the Levi-Civita symbol is defined such that if all 3 indices are different, it's equal to either plus or minus 1, and if any 2 indices match, it's equal to 0. So for example, epsilon 1, 1, 2 is equal to 0 since the first 2 indices match, whereas epsilon 1, 2, 3 is equal to 1, and it will turn out that epsilon 1, 3, 2 is equal to minus 1. If none of the indices match, the rule for determining if the value of the symbol is plus or minus 1 goes as follows. Imagine arranging the numbers 1, 2, and 3 in a triangle like so. If the numbers are oriented in such a way that reading them off in order, so from 1 to 2 to 3, moves clockwise along the triangle, then the value of the symbol is +1. If the numbers are oriented counterclockwise to the triangle, then the value is -1. Formally, what we would say is that the Levi-Civita symbol is totally antisymmetric about a swap of any of its two indices, meaning it just swaps its sign when you do that. Notice that this means that if we sort of rotate the indices, so we shift 2 and move the other one to the other side, this doesn't change the sign. So why is this useful? Well, it turns out that there is a very neat way to express the vector cross product using this symbol. You've probably seen the cross product before. If we have two vectors v and w, then their cross product has a magnitude which is the area of the parallelogram between them, and it points in a direction perpendicular to both v and w. This is the geometric definition, but like the dot product, there is an algebraic definition. Unfortunately, unlike the dot product, the definition is a little ugly. Now, this can be simplified by writing the expression as a determinant of a 3x3 matrix, but this is still kind of clunky. It would be really annoying to have to write out a matrix every time if you wanted to work with a cross product in its component form. But if you look really carefully, you might notice something interesting. Let's take a look at the z component of the cross product. We only have two indices, 1 and 2, which correspond to the x and y components. We then sum those, but when we swap the order, it introduces a minus sign. These properties are very similar to those of the Levi-Civita symbol. If you fiddle around with it for a while, you'll actually find that this can be written with it, where e hat 3 is just z hat. So using Einstein's convention, we can even drop the sum, just leaving a very nice compact expression, epsilon ij3 ai bj e hat 3. Let's check that this works. Remember that I and j can sum from 1 to 3, but if I equals j, then that term goes to 0, so we would disregard those terms. Similarly, if I or j equal 3, then the symbol will be 0 as well. Then there's only really two non-zero combinations. I equals 1 and j equals 2, and the swap of that, so I equals 2 and j equals 1. And you can check for yourself that this procedure will hold the same for the x and y components of the cross product as well. So using this, we have a very compact form for the cross product. Just replace 3 with k, and again, k gets summed over now because it's repeated. Okay, so we've finally assembled the most essential building blocks to work with Einstein notation. The notation itself, the Kronecker delta symbol, and the Levi-Civita symbol. We've talked about multiplying vectors together, so what if we try multiplying these symbols together? We'll start with the delta. Say that we have 4 different indices, I, j, k, and l. Then it's not super interesting to say we multiply 2 deltas with these symbols, because this just says that we have to match I and j and k and l. Otherwise, it's 0. And if they do match, then it's 1. However, what if one of the indices matches? So I'll replace k with j and then l with k. Now, since j is repeated, we know implicitly to sum over j. However, suppose that the value of I is, say, 1. Then the first delta says that the value of j must be 1 as well. But then this requires k to also be 1. So we can actually contract this and say that this is just equal to delta ik. This is a nice little property that you might have immediately seen if you're someone that's exceptionally clever. So the Kronecker delta is actually pretty simple to work with. What about the Levi-Civita? Well, unfortunately, the identities here are a little bit more annoying to derive, and I don't think it'll add too much to the video, so I'll just show you. It's a 3x3 matrix. Pretty overwhelming, but luckily we don't have to deal with this mess that often. In practice, most of the time what you really care about is if 2 indices match. I'll choose to set n equal to k, then this whole determinant just simplifies the expression down to this. Okay, so it's better, but maybe still difficult to remember. But there is actually a simple rule that will let you reproduce this every time. So notice that in the first term, what I've done is just to match the first index on both Levi-Civitas, and then done the same for the second index. Then for the second term, there's just a minus sign, and I've swapped the order. And that's it. I've just given you the basic rundown of index notation. You can use the basic principles presented in this video to work with vectors neatly and compactly, and often to prove some pretty nasty vector identities. So for example, the background is now running a proof on one of the more commonly known identities, the triple product, otherwise known as the back cab rule. I'll spare going through all of this explicitly as this video is already getting a bit long. If you'd like to practice, though, I've left some problems in the description for getting a hang of things, and I hope all of this helps you with your struggles.